Swayam Prabha. Digital India. Educated India.
Good day everyone, and today we will continue with the module 4, which is texture representation, and today is lecture 17, in which we will show the symmetry effects on orientation matrix. So, let us start. So, the concepts that will be covered in this class are rotation or orientation matrix. Second, crystal symmetry effects on orientation matrix. In the previous lectures, we have understood what is an orientation matrix, which is also known as rotation matrix, right. So, a orientation matrix is basically related to orientation, right. So, what is an orientation? Orientation is the relationship between the sample and the crystal coordinate system. So, if a crystal and the sample coordinate systems are known or is specified, then we can find out the relative angular positions of the crystal coordinate system with respect to the sample coordinate system, and this is basically known as orientation, right, or a specific texture, right, a specific texture component which can be given by G. So, usually we show that by G, right. So, the relationship between the crystal coordinate system, which is C c, is equal to G, which is basically the orientation times the sample coordinate system, right, C s. So, G, which is the orientation, can be expressed in terms of basically the most basic thing is using Miller indices. So, we can use Miller indices like planes and directions to show it, and we have discussed about it earlier in earlier class. And Miller indices is shown by using two tools specifically in texture, and that are pole figures and then the inverse pole figures, right. So, the other way of expressing the G is the Euler angles, right. So, we use Euler angles phi 1, phi 2, and then we can plot that in Euler space and show them as orientation distribution functions, we call them ODFs, right. The another way of expressing G is axis angle pair and Roderick space. So, basically these are the important tools by which we express the orientation that we are obtaining in our experiments, right. So, but the most fundamental way of expressing G is the rotation matrix or the orientation matrix. And what is the rotation or the orientation matrix? It is the rotation of the sample coordinate system into the crystal coordinate system, and that also we have seen in the previous lectures. So, what is it? So, G is basically equal to the matrix which contains cos alpha 1, which is the relationship between the sample coordinate system R d, that is the rolling direction, with respect to the specimen coordinate system 1 0 0, the crystal coordinate system 1 0 0, right. In this way, when transverse direction is related to the crystal coordinate system 1 0 0, it becomes cos beta 1, and like that when the normal direction n d relates the angular relationship with 1 0 0, it becomes cos gamma 1. Like that, the R d, T d and N d can be related to 0 1 0 to form cos alpha 2, cos beta 2, cos gamma 2, and with 0 0 1 to form cos alpha 3, cos beta 3, cos gamma 3, right. So, this is the way that an orientation matrix is defined, and the orientation matrix, the cos alpha 1, cos beta 1, cos gamma 1 and all the other 9 variables are basically shown with respect to G 1 1, G 1 2, G 1 3, G 2 1, G 2 2, G 2 3, G 3 1, G 3 2, G 3 3, like this in the matrix. And what are these? And as we have seen that it is the relationship between R d, right, T d and N d with 1 0 0, 0 1 0, 0 0 1, then we have found out that of course, then this G 1 1 is G 1 1, G 2 1 and G 3 1 is basically related to R d. So, if the Miller indices of R d is U, V and W, then the G 1 1, G 2 1 and G 3 1 is U divided by root square of U square root over U square plus V square plus W square, which is given by N 1, right. Like that, it is for the G 2 1 and it is for the G 3 1. On the other hand, if H k L is the Miller indices for the N d, then H divided by N 3, where N 3 is basically root over H square plus k square plus L square, is basically the G 1 3, right, and like that k by N 3 is G 2 3, L by N 3 is G 3 3, right. So, this is the relationship between the Miller indices and the orientation matrix, and which we clearly understand. On the other hand, if we take the middle column sorry, and that is G 1 2, G 2 2 and G 3 3, and this is the T d direction and could be given by Q R S divided by N 2, and where N 2 is basically equal to root over Q square plus R square plus S square, right. So, you see the orientation matrix basically expresses the important sample reference direction in terms of the crystal direction that are parallel to them. That means that U, V, W are parallel to R d, Q R S is parallel to T d, H k L is parallel to N d. It represents the important sample reference direction in terms of the crystal directions that are parallel to them, right. So, you see, if we look closely to the orientation matrix, you can find out that both the rows and the columns of this matrix are unit vectors, right. So, if you add them, it becomes, if you add the square of them, it becomes unity. So, you see that this matrix is basically orthonormal. So, the inverse of the G matrix is basically equal to the transverse of the G matrix, right. So, moreover, what we understood from this study is that the orientation matrix basically contains 9 non-independent variable U, V, W, Q, R, S, H, K, L divided by their respective square roots. The cross product of 2 rows. So, cross product of 2 rows gives the third one, right. So, a cross product of N d cross R d gives T d, T d cross N d gives R d, right, R d cross T d gives N d, right. So, you get the third by using the cross product, and for any row or column the sum of square becomes equal to unity, and that is why its G inverse is equal to G transpose, right. So, basically what we understood from here is that the orientation matrix, which is basically given by G, is most of the time expressed in terms of Miller indices in form of pole figures or inverse pole figures. It is expressed in terms of Euler angles in Euler space, mostly in form of orientation distribution function ODF. otherwise it is expressed in terms of axis angle pair or Rodrigues space. We have also seen that misorientation matrix, that is delta G, which is an homologous to the orientation matrix. The orientation matrix is the relationship between the sample coordinate system and the crystal coordinate system, whereas the delta G is the relationship between two crystal coordinate system, adjacent crystal coordinate system. Like for example, in a polycrystalline material, if there are presence of different grains, the relationship, the misorientation relationship between the two grains will produce a matrix delta G, which will have the same 9 variables like that, like in the orientation matrix, and therefore, we can represent that in terms of Euler angle and in terms of Euler space, and in this case it is known as MODF, that is misorientation orientation distribution function, and we can show that in terms of angle axis pair, and we can show it in the angle axis space or in terms of Rodrigues vectors or in the that means in the Rodrigues space, right. So, you see, so based upon the crystallography, that means the crystal structure and the crystal symmetry, there could be many related solutions for a single orientation matrix. That means, there could be a number of orientation matrix, there could be a number of solutions, right. So, the orientation matrix depends upon the angular relationship between the crystal and the sample coordinate system, and a number of solutions may exist because there are crystal symmetry and sample symmetry. And what do you mean by crystal symmetry? Because the crystal has point group or space group symmetry. So, mainly here we are talking about the point group symmetry, that is the rotational symmetry, and the sample symmetry. The sample symmetry depends upon the type of process that the sample has undergone. So, whether it is a rolling or a particular kind of a casting. So, each will lead to have a certain kind of symmetry or no symmetry in the sample, and thus the requirement of symmetry is the understanding of the symmetry, crystal symmetry and the sample symmetry is required to understand that there could be many solutions that may exist to show a particular orientation, and that means there could be number of orientation matrices based upon the crystal and the sample symmetry, which show the same orientation. So, let us start with a nice example considering the crystal symmetry for cubic crystals. Example is the ND plane is 1, 2, 3 bar and the RD is 6, 3, 4. So, you see that if we take this example and we try to draw the orientation matrix G relating 1, 2, 3, 6, 3, 4 with RD, TD and ND, whereas 1, 2, 3 is basically ND and 6, 3, 4 is basically RD. So, you see that UVW divided by N1, the N1 is basically root over 6 square plus 3 square plus 4 square, which comes out to be 61. So, root over 61, and so 634 divided by root over 61 gives the first column of the G matrix. The third column of the G matrix, which indicates ND, is given by 1, 2 and minus 3 divided by 1 square plus 2 square plus 3 square root over. So, which comes to be equal to be 14, right. So, we do the cross product of ND and RD, and we can find out the value of TD, which comes out to be 17 root over 854, 22 root over 8 over 52, 9 divided by root over 854, right. So, this is the orientation matrix corresponding to the Miller indices, that is the texture 1, 2, 3 bar 6, 3, 4, right. So, 1, 2, 3 bar is N d, 6, 3, 4 is R d. So, you see that I have said that depending upon the crystal and the sample symmetry, a number of solutions of the G matrix can exist simultaneously, right. So, let us consider the cubic crystal. Now, cubic crystal, if you look, that there are 24 different ways the crystals of the cubic symmetry can be arranged. Now, this can be find out even from the stereographic projection. So, if you look into the standard 100 stereographic projection, and you see that the stereographic projections is basically divided into a number of triangles with corners 100, 011, 111, and there are number of triangles having the same corner, you see 001 bar, 101 bar, 11 bar, 1 bar. So, each of them consisting of the family of poles for the family of planes 100, 110 and 111. So, you see that if you look in this quadrant of the stereographic projection, you can see 1, 2, 3, 4, 5 and 6 triangles like this. So, if we multiply this 6 into this 3 into this 4 quadrant, then 6 into 4 is 24, right. So, there are 24 different ways the a particular orientation or a particular texture component could be observed in the stereographic projection. Now, there is a different way to understand this thing. So, if you see that what are the 24 crystallographically related solutions for the orientation matrix, you can see that it has 4 111 axis which has 3-fold symmetry, right. So, you see if we give 2 rotations by 120 degrees about the 4 111 axis, it goes to the new position, but the crystal looks exactly the same, right. On the other hand, you see it has 3 110 axis with 4-fold symmetries. So, if you see that if we give along a 100 axis, okay, if you give a rotation by 90 degree, it comes exactly to the same, it looks that it has not been rotated, right. Like that you can give 90 90 90 rotation and it will be always look like the same. Similarly, it has 6 110 axis with 2-fold symmetry. So, if you give one rotation of 180 degree along any of the 100 axis, any of the 6 100 axis, it comes to the same position. So, you see and there is the position where there is no rotation, that is the identity matrix, right. So, you see that if we add like the first one, that is the 4 into 2, that is 8, and then 3 into 3 for the 100 axis, that is 9. So, 8 plus 9 is 17 and 6 into 1, that means 17 plus 6 is 23, plus the identity matrix becomes 24. So, there are 24 crystallographically related solution for the cubic crystals because of this kind of symmetry element, which is point group symmetry, which is present in it. So, okay. So, if you note that there are 12 and 4 solutions for the orientation matrix for material having hexagonal. So, there are 12 solutions for the hexagonal system, hexagonal closed packed system, and 4 for the orthorhombic symmetry systems, right. Similar, and the similar solutions can be obtained by observing the similar kind of explanation. So, you see that let us go to this cubic crystal and see that for the 1 2 3 bar 6 3 4 kind of texture, how 24 different crystallographic solutions can exist, right. So, let us go. So, you see that if we look into the family of planes for the 1, 2, 3, right. There could be 1, 2, 3 bar type plane, right, which is this one, and there could be 1, 2 bar 3, and there could be 1 bar 2, 3, there could be 1, 2, 3, and these all 4 planes are different planes, and related to which the direction, which is basically R D 6, 3, 4, which is for this particular, the combination could be determined because the R D lies in the N D plane, right. So, let us say there are 4 combinations that can be determined, right. Now, for each combination, let us talk about this one 1, 2, 3, 6, 3, 4 bar. We can find out, you see, by changing the position from 1, 2, 3 to 1, 3, 2 to 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1, like this. By changing the position, we can find out the values of R D, which will also change positions accordingly. So, there are how many solutions? There are 6 solutions like this for this particular by changing the positions of the Miller indices, and then like that we can do it for all the 4 of them. So, you can see that there are 24 crystallographic solution for the same texture, same orientation. Now, for each one of them there will be a different, you see, the orientation matrix. So, you see for 1, 2, 3, 6, 3, 4 bar, it is, you see, 6, 3 minus 4, 1, 2, 3, of course, divided by the root mean square of their value, right, and then you see the T D is minus 17 minus 22 9 divided by root of 854. If we take another one, and of course, which is this one, you see there is a subtle change here, 6 divided by root of 61, 3 and 4, right. On the other hand, 1, 2 and minus 3, and of course, it will happen like this because the position of the Miller indices are changing accordingly for each of these 24 cases, right. If we look into the another case, it shows the orientation matrix slightly different from the other one. So, each one of this HKL UVW texture will have a different Miller indices, and here is another example. So, we have given 4 examples, and one can find out for each one of these 24 cases different orientation matrices, right. So, you see that there is subtle differences in the sign and the positions, and therefore, each orientation matrix is different, and this shows that these different Miller indices representing different matrices contains or show the same orientation, right. Now, each of these matrices holds a different position in the Euler space. So, when we are looking into the Euler space or orientation distribution function or ODFs, we will find that for each of these Miller indices or each of these orientation matrices, there will be a different phi 1, phi 2 in the Euler space, and all those components in the Euler space seems to be repeated many times, but it will represent the same orientation, and this occurs because of the symmetry of the cubic crystal, and it will occur the same for the hexagonal and the orthogonal symmetry systems, but for hexagonal it will be 12 crystallographic solution, for orthogonal it will be only 4 crystallographic solutions. So, the conclusions are that orientation matrices are the most fundamental means of expressing the orientation or the texture components, right, and these orientation matrices could be related to the Miller indices via the pole figure, or the inverse pole figures, right. It could be related to the Euler angles via the Euler space and the orientation distribution functions ODFs, and it could be related to the angle axis pair through Rodrigues vectors or Rodrigues space, right. There are 24 solutions for orientation matrices in cubic crystals, right. There are 12 solutions for orientation matrix in case of hexagonal crystals with hexagonal symmetry, and there are 4 solutions for orientation matrix in case of orthorhombic symmetries. Thank you very much.